Open up, you can see the board, Nandi. Okay. Um, um, so today's video is going to be very important. It's basically on today's date is the 9th of January, 29th of February, 2026. The time now is 1:22 a.m. But I've got this board here, so let's make use of it, Namdi. What are you saying? So you are just for yourself to do it. These AI systems. So github.com/OB Nexus, O for Oscar, B for Bravo, I for India, N for November, E for Echo, X for X-ray, U for Bella, S for Sarah, /patents, P for Papa, E for Alpha, L T for Tango, E for Echo, N for November, T for Tango, S for Sarah. Pattern repository, this is where the AI system is, OBI AI. Ontological, this video is on the NSIGII, N for November, S for Sarah, I for India, G for Golf, I for India, I for India. But this is basically the Human Rights Protocol. OBI are both ontological, Bayesian, intelligence, infrastructure, OBI infrastructure, architecture, okay, so basically OBI stands for ontological, Bayesian, intelligence, architecture. Architecture refers to the terms how it's built. If you're an architect, you're curious about how things are built, how to what, why, when, where, why. This is the video on architecture as infrastructure, ASI, where architecture is how we build stuff. The architect of a computer, human rights computer, like NSIGII, like Luca West. The architect builds how to what, when, where, why. But this video is on the architect beginning via program. So architects build, but they have targets. Infrastructure is architecture, but it is built for one target, one demographic. So you got the ontological basic architecture as infrastructure, A as I, and you got infrastructure as architecture. Built for a demographic of people, like Chinese people, Igbo people, based on target operating systems. But I'm going to do this video because I've been doing the whole video for a long time. But it's very important because of AI, artificial intelligence, including clipping. Yeah, so we're gonna have T1 equals 60 seconds. Let's say 5 minutes. T1 or 30 seconds timer, the consecutive timer, 30, 15, and T1 30, T2 15, and T3 T3 T sub 3 equals 10 or equals no 10. So 10 seconds. You have to try it for 5 seconds. T equals the time. T equals the time. Or to change the time 4 seconds. So 30 seconds. I have 5 seconds. 5, 10, 15. But I'm trying to do 5, 10. So 10 seconds now, because I'm trying to do a different one. So 5 times 2 is 10. 3 times 5 is 16. And 30 is 10 times 3. Yeah. So we're gonna start with this model here. But the goal of this video is to talk about what's on the left hand side and express it at the right side. As the right side. So this time is basically the time to introduce the Guinea AI system. But you get in NSIGII, OBI Guinea. So Guinea is a master. So Guinea is a parrot. GINI. G for gold, gold, I for India, N for November, I for India. But it's part of the project of actually what. So Guinea literally means what in Igbo. West Ham AAT West. West Ham Alpha Tango. Guinea G for gold, I for India, N for November, I for India means what? Literally, it means what? But the time is consensual. So it's a consensual AI system for human rights as a protocol. It's basically an ontological architect behind its own mind. it probes the source and resolves something. Because I want the AI to run adapt. I don't want to limit the AI system, across the match them. So T1 within 30 seconds. That'll be 30 times 6. Which should be the 3 times 6 is 1800. What is 80,000 seconds? 15, no, 3 times 6 is 18. 15 times, 1.5, 15 times 6 is 1,500 seconds, and 10 times 6 is 16,000 seconds. 600,000 or 500,000 seconds. So you get 60,000, 100,000 seconds. You get a system here that works for people, but it's basically a filter flash sequence. So I'm going to do it slowly. So we have 4 categories of filter flash sequence, but basically it's a symbolic Trident resolver. To get yes, no, maybe. So the computer holds on purpose, but that hold is a yield. So basically, it pauses, but it's a full hold state. It holds on which the user input. Basically, it yields something. It doesn't pause. It holds mid processor. So there's a difference there. It's a consensual. It's consensual. Yielding is usually holding something in memory to resolve, but yielding is not a hold state. It's not. It doesn't terminate the state. State. For example, if I say yes, if you give me consent, say I'm going on a cookie website. If I get a cookie, do you want a cookie? I say, you say no, yes. I say, and I cook, and I say, and I wait. I'm not sure. I'm still processing. I'm processing. A yield state, well, what yield to the processing is done. You can have a time to apply. But basically, this is minus infinity of the program. So you can have yes, which is equal to 1, no equal to 0, and maybe equals to minus infinity, minus 1, infinity. Infinity cancels by 1. So infinity to negative 1. So it holds indefinitely, but there's 3 resolvers to it. So yes is a 1. This maybe is progress. So if I can say yes or no to a cookie, I can get maybe, which basically targets infinity of the system to the power of negative 1. But if you have to try to multiply, you're going to have a concentration of minus 1 to the power of 3. For me, myself, and I. This basically means the system holds for itself. Me, the system, me, beginning. So the beginning is a future system. So it's holds because there are 3 states that resolve and 3 ways you can hold. So this is a hold. It's an interdependent hold state for a non-deterministic function automaton. It's hold because it needs to hold for the user. It's basically a consensual AI system because the AI must wait to the user, until the user can give an input that's coherent or coherently classifiable. Basic consensual need, consent and consensual. So you give you consent and consensual. So consensual means you need to fit between parties. The party should be you or me, but me, if I need food, I give you. But it's basically Guinea cursor or Guinea pointer, points to your need. It has to hold your need, but it's a pointer. So it's just a pointer. Giving pointer to mouse pointer. Guinea is a pointer, and Guinea is a parrot. So if you go to GitHub, the account /obs obs Guinea, you get a pointer now. You get a start question. So you get now get to the points now. I'm going to fit in here. So because symbolic, so we got a standard kind of Alexa partner system, but this one here is based off. So I'm going to start here. We got a symbolic statement. The statement is symbolic. So you have, let me wipe the board. You have a symbolic statement, a symbolic expression. You have a symbolic statement. A symbolic statement. You have, for example, you have something. So in English, you have diacritic. So they're like diagram. They are directed, but it's directed symbol. So a diacritic, like A, E, I, O, U, is tonal. Tonal. It's tonal. A is basically a high tone or low tone. But this is basically the defining symbols of Igbo or philosophy. These symbols that have low tones are called glyphs, glyphs when they switch characters. You get 36 letters in the English Igbo alphabet, 25 plus 1, 8. Uh, you have 36 alphabets, but in English Igbo alphabet, you get 34, you get 36. 36. So 36 is basically Igbo alphabet. So you get A, I, O, U. High tone, low tone, a high tone, A, E, I, O, U. A, E, I, O, U. A, E, I, O, A, E, I, O. Because the word Eze, if at the high tone and low tone, means to high, when E has a high accent, and then Z has no accent, and Z has a E has a low accent, means teeth. And this means teeth, like this is your teeth. So this just means teeth. This is the word teeth in Igbo. Eze, we got Eze, high low to high tone, E-Z-E. The accents for T and K are diacritic. So it's a diacritic resolver of vowels, because they can be tonal based on the context of the system. So basically, it's a resolver. So you can have two interpretations of it based on the target language. If the character set is Igbo, if you have two character sets like French, if you speak English and Igbo, you will know that Igbo is a tonal language, English is not a tonal language, but English does not have accents. So English has, like Igbo, these accents too, but it's a tonal system, so it's a filter flash system. Filter and flash system, The symbolic system works by having a data drift model, a data drift mitigation. This is AI. So data drift refers to the idea of data being drifted, data. Basically, we have a lexical analyzer. For example, a lexical analyzer that has a lexical analyzer. So if you take a tripartite lexical analyzer, this can mean it can indicate some terms. So you have Alexa or lexical analyzer has either Cisco what has not Cisco what Cisco has what I say was the symbolic state. The symbolic state. Yes, it can be it's a valid token, invalid token, or user defined, system system user defined token or systems token. No. But this token means that other characters. You can have I know this is this character. It's a valid symbol. It's a valid symbol. It's an invalid symbol. It's an invalid symbol in the symbol registry. So it's basically has to model like the kind of way natural language operates, but which is in symbols. But it's basically computational language model. Because of consensus need of business to field water shuttle. So you have a different system of kind of validity of system. But user variables are, or you can have user defined or exported or built-in symbols like of capitalism. This is called a uniform chemical normalization. Uniform, like it's uniform. They share the same lexa. Uniform canonical means they share the same system. So uniform means they have a tripartite resolution of yes, no, and maybe. And canonical means they share the same canicality of domain-specific systems. For example, the domain Alexa. Alexa is basically a type of lexical analyzer that identifies words, the also words. It works on tokens. They identify four categories. So the four categories are the lexical analyzer. But this is basically a symbolic statement. A statement that means yes, no, and maybe. And the tripod, the little three kind of states yes, no, and maybe. Yes, no, and maybe. Am I right? So system must keep holding space with a negative one. The yes is a one, the no is a maybe, and the infinite minus one for the state is tripart. So this is infinite memory. So infinite time, infinite space. Q minus one Q for space time and user defined systems of space and time. So auxiliary constructions of the user. Basically, this is a philosophy of ensuring the endiness of a system is tripartite, but the minus one holds the space and holds on that space until the user clearly defines that structure. It cannot ghost you. It's a no ghosting policy. So basically, it cannot ghost you what you need until it's clearly defined the accident. Because you get minus one times minus one. So minus one for space. Space looks like 512 bytes of data. 512 bytes divided over the period of 30 seconds. Over 30 seconds will be 8 times 5. 8 times 5. 8 times 5. You get 6,000 times 30 seconds, which would be 1,800 seconds. 1,800 seconds. 800 seconds. 30 seconds over the bicycle. Which space the time ratio? The space with the bicycle. You get 700, you get 500, you get same thing divided by 15 seconds. If you need, but the space you have is infinite. You can keep adding, you can keep accumulating more space just by typing it in. And the more time you have, do you need more time? Yes. What the time you need, and that time comes an input to the next system. But this is just like a simple system. To determine when the next halt. You can also cancel it. You can also cancel it, of course. So if I say, do you want food now? Since I say yes. Do you want food later? Yes or no? Past here and now philosophy of here I want food, now I want food. Here I want food. This is to allocate food. Here's of SMT, TP, hopefully. But to here now philosophy, I am here and now. I'm here and now. And so we need this. And he says, this is actually tracking you. Understand? It's a GPS code system. Basically, so I'll come back to the new one because I had that before. But it's a here now philosophy for spatial models of uniform chemical character sets. Character set. Because the character sets refers to the idea of heterogeneous, we need to share the heterogeneous, homogeneous character sets. So what I mean by this is they have a here and now, of course, and now and here, but they share, okay, a woman is a type of man, is a, no, you have structure, so you have four, in the heterogeneous structure, you have four categories. In category theory, I'm defining this formally, so listen properly. So you have a heterogeneous homogeneous state of data. So you have I didn't go wrong my pen off now. We'll go paper. No, I'm just getting paper, show it down. But you have four categories. You have basically you have four categories. So this idea came about by type 1. You have a type 1 error. You have a type 2 error. On type 2. So you get type 1. So you get true positive, false positive, false negative, and true positive. So you get false positive, true positive, false positive type 1, and true negative is type 2. That's fact. But this is actually heterogeneous to one result. So basically, you have a false pre-mapping because it's kind of heterogeneous homogeneous classifiers. So how this works is the baseline is heterogeneous result because of this QA matrix, quality assurance. This is the baseline of the heterogeneous model. But the baseline is literally classifying categories, put it in categories. Including categories that also point to for the consensus state. So the consensus will maybe the system acting up. So how this works basically, you have a true negative negation of minus one here. You have to hold space, three space, false negative. So you hold this space indefinitely, and use the states minus one minus one. Listen, this can be maybe I'm wrong here, maybe I'm wrong here, maybe I'm wrong here, maybe type one, maybe type two. And for example, a woman. Example of the statement is a uniform statement. A woman of citizenship. A girl. A girl is a type of data, a token type of data in the system of woman or man or man. You see, so the categories are woman and man. Where does the girl fall in? So the categories are this man. So if it's the woman. So Andrews identified two categories. So you get two sets of the symbol. If a woman is literally, so you get two sets of. A girl is a type of woman. Yes or no? Yes. This would be. So a girl is a type of woman. A girl is a type of. Is a girl is a woman? Yes. This is a prerequisite in action. A girl is a type of woman. Yes. So this is here a true positive. Yes. So a girl will be here. Yeah. A girl, a young woman, a young woman is no. A girl is a type of woman. A girl is a kind of woman. Yes. This would be yes. So this is the kind, the model. So yes. So if a girl is a type of woman, a girl is also a kind. So you get four states. You get four states. You get token kind, token type, token type for the token value and the token memory. You got token kind. Token kind. So the kind of the data. The kind of the heterogeneous model. So this is into type versus the kind. So you get two folks. You get like 40. Let's just roll this out and do it again. Let me do it properly. So you get kind of categories. So let me try to do 1, 2, 3, 4. So you get a token kind, true, positive, false, true, negative. So you get two sets of it: true, false, positive, false, negative. So a girl is a type of woman. So basically, a girl is a type of woman, and a type of woman will be false. A girl is a type of woman. Is that a false positive or true negative? A girl is a type of woman. Yeah. So a girl is a type of woman. So if it's a category of a girl is a type of woman. So the type of woman will refer to a true positive. So true positive. Yeah. So yes. So basically yes. A girl is a kind of woman. Yes. So you get two. That's the type of count. A young girl. A girl is a kind of man. A girl is a kind of man. Because all women. A girl is a type of kind of man. Yes. So the first is true positive. So you get the check true positive. Yes. It's true. This is true. This statement is true. It's true. It's valid. It's valid. Because the type of woman, a kind of woman, the type of woman, a kind of woman. So the young girl, a type of man, and a kind of woman. Because the term man is BiPartite. You get a woman for a man. You get a woman which is a man, but it's a BiPartite resolver. So basically, it's two states. It's BiPartite. So this category is true. It can have this one. Beauty. All men, all women, all men are beautiful. Are beautiful. Beautiful. Wrong. This one is false because a woman is I call it beauty, but men are handsome. So this one will be handsome and beautiful to BiPartite, handsome woman and man. So a man is beautiful will be wrong. So this will be a man is beautiful. A man. So because a man is a type of woman, a man is beautiful. Yes, a man is beautiful. Yes, all men are beautiful. All men can be beautiful. All men should be beautiful, and all men can be beautiful. A man is beautiful will be yes, true positive. So will be here, true positive. So men are beautiful, true positive. All men are beautiful will be here, true positive. But this all so basically this is basically all women. So this is all women are handsome. Okay, some all women are beautiful. It can be true or false, but I don't really know. Bible says, "I just the term, who's the term? All men can be considered beautiful. So all men are handsome. All men can be considered handsome, because the term handsome is half beauty. You get a half beauty, so you get a half. So the term handsome refers to the how you reference them. All men are handsome. But handsome is the man's equivalent of beautiful. So you get a bipartite topographic state of a topographic state of mapping. So segregation. So because a woman is beautiful. A woman is beautiful. Will mean for a woman is handsome is true, but a man is beautiful is not always true. About a man. Sorry, a man is beautiful is false. False. A man is beautiful is false, but a man is handsome is true. So men are handsome, not beautiful. So women are. A man is handsome, true. A man is beautiful, no. Unless you identify as a woman. Unless you identify as a woman. So it's a bipartite resolver. It's a bipartite resolver to resolve the kind of heterogeneous, homogeneous data of classification or category theory. Next, so it was category theory. So it wasn't categories. Not heterogeneous means like you have four kinds of data that fit in classifier of the kind, but you have two sets of that data set at a time, token type and token value. Now, to give you the max formula. So you have the symbolic statement. Now you see the expression. So the expression reverses to the kind of idea. You see expressing some kind of a thing. So the expression is true or false. So the symbolic expression expresses three results. Three models, three poles. They're called poles. They mean something, but the poles have a meaning, anchors. So the kind of system I mean it's like so you have three needs, wants, wants, and could, could. You could do that. You could, you should. No, you could, should. You basically, it's a point system for need, should, and could. Need, should, and could. You could, you could. But this infers want. So you want, you need. You get three. So you get three resolvers. Basically, signifies three resolvers, three times. You need, a should, and a could. Three expressions. The expressions are because of the parts. You get a lexer, a bipartite lexer. You get a heterogeneous lexer. You get a heterogeneous homogeneous parser, which infers the meaning of the executed instruction set. The lexer are just a terminology that refers the parser system. So you get a system of resolution, calculation. What I write here. So the system must ensure that the needs are met, and the needs are literally are completed ahead of time because you got encoded for suffering. So I'm gonna take my notes now and read it. So here I'm gonna case now. Okay, 1 second. Let me use the toilet, guys. I'll be back. Let me pause here. So I'm back now. So basically you get but this is very important. So this has to be not this has to be a dynamic system. This is the shift. So basically I've got this working mathematically too. So here I got my notes, guys. So here is n summation of I, where I is suffering. Summation of I. equals M, which is need, minus R, which is the resources, computational resources like space and time, and in brackets times K, where K is a constant coefficient of suffering. So so I'm going to turn the board now and give you an example of this system here. But we gotta resolve this with the third one, the illustrated understanding via symbolic intent. So let me go and stop it. Let me just go and play the board here. So I'm going to play the board now. So these are called problem categories. But choose to have it one layer down. So this can be a Lexa problem, heterogeneous, homogeneous Lexa problem, homogeneous Lexa problem, lexical problem, or a partial problem. But these problems are shared problems in the domain of identifying the kind of system of change. But mathematically, it's sound. It makes sense. You can't disprove it. It works as a mathematical principle. It's still foundation. So I'm going to write the formula for happiness formula, and we're gonna work on this very well, very well. We're gonna work on happiness formula here. Am I forgetting anything? Yes, I am. Yes, I am. So I'm gonna put it at some point too. So we're gonna have happiness. Happiness is defined as H equals S plus plus S plus T plus V. S plus C plus V. S plus C plus V. Oh, circumference of. So happiness equals to S plus V. This is a form for happiness. But we're trying to code suffering into the system. So we're going to compute suffering. So you get happiness, H is happiness. S equals S equals set points. Stable set point of your current status. Your set point of your happiness score. Basically, there's a point here and now defined in space. For example, to me, your point here and now. One first set point versus set point. For example, you have a mapping of happiness of 1 to 2 pi. 2 pi. So 2 pi results in 1. So this is one set point. One's full set point. But 2 pi is 2 pi times 180 times to bring 2 pi to the 2 pi divided by r, 2 pi divided by r to times 180 to 2 pi divided by r to 2 pi squared, 2 pi to 1 2 mapping. So one define one set point defined as 2 pi r divided by 180 times 2 pi divided by r, 2 pi divided by 1 unit of radius times pi, no, 2 pi pi r, pi r divided by 180, pi r, 2 pi r squared, 2 pi, 2 pi, 2 pi divided by r, and pi r squared. No, pi divided by 2r, 2r, pi divided by 2r, pi divided by 2r, mapping to pi r squared divided by 180. And this is separate. So the separate is formal. You get a circumstances. Circumstances that gave you that pi. So the circumstance is defined as the current state of being over x squared plus y squared equals t squared. Now t squared is a change in is one t squared is 1 over square root of v squared plus c squared. the changing, the changing one squared or t squared is the changing one squared, one divided by the square root of r squared plus c squared. No, sorry, the square root of v squared, which is the vector point or the vector, the change in basically, this is basically time direction formula. This is Lorentz factor. Lorentz factor. So you get y squared, which is negative b plus or minus square root of b squared minus 4ac over 2a. This is the equation, but x is basically the x is basically the first input. There's the match between system between 2.1 over 1 set point, one solution of the second. But x can be a parameter, a range, or an area. So the circumference C is defined as the area. So if the x is an area, x is a parameter, the C, the circumference will be the tangent line that touches the tangent line. The circumference will be the tangent line that touches the second line will be an area or segment of the set point, a segment of it. This will be pi 2 pi r, or 2 pi over 1 2 pi r. So this will be pi r squared over pi r squared, pi divided by r squared to r squared divided by 360. Pi r squared. Pi divided by r squared to pi r squared divided by 360. But still has to remain coherent. No, coherent. So the coherent score is a very important switch. So you get this one right here over 360. So the second square is pi divided by r squared mapping to pi r squared to pi r squared on 360. And you get the baseline model. So the voluntary action of the user. Can the user volunteer? Now, the voluntary is very important to understand that it is it's a constant switch. Now, this is what defines the baseline. So, if the baseline of suffering, so the constant switch are basically based on the coding of the baseline. So, this baseline will be if R, so suffering from suffering. So, yeah, I've stated the system has reverse of happiness. But we're gonna have to compute the inverse of happiness to have it. So to have suffering. So suffering is according to the system, so the system can know what suffering is. But it's a symbolic expression tree. Symbolic expression tree will give you three states, yes, no, and maybe. And the poles align to those states. For example, you have the suffering question I, because if you hate to get I, if you get hate to get I. I is suffering, is equals to the summation of n need minus resources times k, where k is the coefficient of the y term given t and x. So the coefficients are taken into amount at that space in time. For the coefficient can be 3x squared plus 3y squared plus 5x plus c times k. So how this works mathematically to encode suffering is you define if x if so how does it work? If the baseline approaches 0, so basically let me pause the screen. Let me get on sim. So if the 1 second let me pause this very. So you're gonna have something I call suffering, but it's basically expectation bound. So you're gonna have something which is defined suffering without so it's need. Need can be so the term categories are need, N for need, W for want, need could, you should, need is should, need is must. But need can imply should, should based on the agency. So this is an agency model. The need is a must, but the must could be a should, because if the user can have agency, or can do themselves, in other words, need should is a want. Should I do it or could I do it? A reply that it is not needed, might be needed or not needed. Basically, it is implicit to expression resolution of a DAG. So, so I'm saying that if resources are more than equal to m, you're suffering. It's more than equal to m. When n is in need, if resources are okay, if the resources is more than equal to the need, then you're not suffering. You're not suffering. But if the k constant collapse close to zero, this was the baseline. The baseline has dropped, and you're now suffering. So that's the formula. So the suffering coding is BiPartite. It can suffer, you not suffer. So the coding again is like the piecewise functor. I'm going to compute over. So let me sit down now and do the maths. So I'm going to come with a sample problem to deal with this now. So my computer here. So I'm going to come with a sample problem. So the sample we're going to come up with is example. Yeah. But the goal is to have filter flash sequence encode suffering via the axis. I'm going to use it. So the filter of flash sequence is like this. So you have the filter flash sequence. But I'm going to do the coding of the system first. We'll try procedure. So you're going to have 1 second, guys. You're gonna have I equals n minus r times k. Equals coefficient. So with this coefficient formula here, now I'm gonna have this encoded into the system. So it was has a state of moderate suffering, and that's basically explicit and implicit state of suffering. But you cannot depend implicit state of suffering all the time. So you're gonna encode that, so you detect that. So because of the platform target or something like that, it has to be encoded. So that's what I'm saying. If you explicit suffering, so you're gonna have I equals suffering, I is suffering, n is need, n equals need, n is need, n equals need, n is need, minus r is minus r was resources times k. And the BiPartite resolution is like a piecewise function. If the powers that works on piecewise functions to resolve basically heterogeneous, homogeneous data. So the puzzle will be if n more than equal to if resources more than if resources no sorry if resources more than equal to m, which is need, suffering collapses equals to zero. And if k implies infinity, if k is a coefficient, k is a constraint coefficient, but lacks agency, cohesion, or entropy, and time pressure, you have infinity. You have this k closest to infinity. So infinity. Then you have this. You have minus infinity or positivity. You have suffering. Regarding of mindset, this is the baseline metric. With k equals to zero, you have a baseline of baseline. So if zero, so you're just suffering, or if k is close to zero, zero. So this is the formula here. I'm trying to evaluate. So let me give you a sample problem. You have x equals x, y, and z. X and y equals need, should, need, could, should. X is x. So y is 3. Let's do 13y minus 15 minus 5x plus c plus 12 plus 12. So you get 13y minus 5x plus 12 here. So if I plug into the quadratic equation, you have this is my physics. You're gonna have to evaluate this now fast. So you're gonna have 13y. So you're gonna get a negative one. I'm just gonna stop 6 seconds, so I can't do it now. But you got the formula now, how to do it. So next video I'll continue, guys.